it's a quick repetition of perturbation theory, or Rayleigh-Schrödinger perturbation theory. The situation is we have some Hamiltonian and we're trying to solve for this Hamiltonian the time-independent Schrödinger equation. And for some nomenclature reason, which hopefully becomes clear later on, I'll call the energy W right now. So that's the energy of the perturbed system. And that perturbation could be many different things. Today it's going to be the electron correlation, which is not included in Hartree-Fock. In a few weeks' time, it will be an electric field or magnetic field, and we come back to those equations then in order to derive expressions for molecular properties. So that Hamiltonian, H consists of, or we split it up in two parts, a zeroth order part and some kind of and this perturbation, and we sort of have a parameter lambda, which either is the strength of the perturbation, and later on when we come to electric fields, that, for example, could be the field strength, and that would be the operator representing the interaction with the field. Today it's actually more sort of a parameter which we can use to turn off and turn on the perturbation. So it has no deeper physical meaning in Möller-Blessed perturbation theory. And sometimes people just don't include that at all and just write the Hamiltonian is H0 plus a perturbation. Later on we will also see the case where we not only have one but two perturbation operators, something which we call first order and a second order. First order and second order because it's linear in the field, and the second order would then be quadratic in the field. But today, in order not to distinguish, we just call it H prime. Now, what is this? How do we do that partitioning? I mean, the partitioning is done in the way that we assume that we know the solution to H0. So for H0, we have, of course, can also write the Schrödinger equation up, where we'll use this notation, and here comes the E. So this is the so-called unperturbed problem. And we assume that we have solved the unperturbed problem, which means we know the eigenvectors, the eigenfunctions, the states, and we know the eigenvalues, the energies of that. So, and obviously if that's that's an eigenvalue problem, so I can run from 0 to infinity. Obviously there's an infinite set of solutions, and this problem can be solved, or we assumed in a way that we have solved that. Which is not always the case. Sometimes it's just an assumption, but today it's actually be the case that we have solved that. And then of course we assume that H prime is in some sense small compared to H0. It's a small perturbation we're treating. So basically what perturbation theory is doing is something which you have seen in, hopefully seen, mathematics courses, or you have seen it. If you think about Taylor expansions, you need to know the value of a function at a particular point, which you actually don't know, but you know the value of the function at a nearby point. And then you expand around this nearby point, and you can do that then sort of with the Taylor expansion, where you have the derivatives of your function at that expansion point as well, and then you can do that. And there is something which is called a convergence radius. The point which you're trying to calculate the value of the function at is only allowed to be a certain distance away from your expansion point. That depends on the function. And if you're within that radius, then one can show, or at least mathematicians can show, that your expansion is going to converge. So if you would be able in some other way to calculate the value of the function with your Taylor expansion to sufficiently order, you will get closer and closer to the real value. if the point you're trying to get is outside of the convergence radius, there's no guarantee at all that your expansion is going to bring you closer to that value. So in that sense, and I mean perturbation theory is precisely doing that. So in that sense, the perturbation has to be small in order for this perturbation theory approach to converge. So the first example of doing perturbation theory, which I'm going to show you, actually doesn't fulfill that, because the electron correlation is actually not small compared to the unperturbed Hamiltonian. But what we do then is not really a Taylor series expansion, but a power series expansion. So our perturbed wave function we expand now in a series where we have a zeroth order term, and that zeroth order term is actually one of those. And let's assume that we're going to look at ground state problems. So we are trying to describe the ground state. So that is actually what we later on will call zero. That's the first of those states, the one with the lowest energy. And then we have corrections. How do we call them? Lambda to the first power, first order correction. Lambda to the second power, a second order correction, and so forth. And we do the same for the energy. The perturbed energy is the zeroth order energy, again lambda to the first power, a first order correction, lambda to the second power, a second order correction of the energy, and so forth. And again, if that is one of those states, the one with the lowest energy, then this, of course, is going to be E0 also. So we expand around one of those solutions. Now, for more technical reasons, one uses, wave functions have to be normalized. And you might hopefully can understand that how the normalization looks like depends on how many terms are included in the wave function. Which means it's a bit difficult to a priori from the beginning write up what the normalization is. And therefore, in the process of deriving the equations, one uses a rather strange kind of normalization, which is called intermediate normalization. Intermediate normalization, which looks like that. Here we have our perturbed wave function, or the expansion of the perturbed wave function. And we don't write up that, we take sort of the overlap between that function and something and require that it's 1, but we don't require that it's actually the overlap with itself, but it's the overlap with the zeroth order wave function, with the unperturbed wave function. Because that's sort of the solution if there would be no perturbation. That's our expansion point, and we correct it by all those. And we require now that the overlap between those two is 1, which is called the intermediate normalization. Now if you insert that here, and of course our zeroth order wave functions, they are all not only normalized, but they are actually also normalized. So the overlap between two zeroth order wave functions is this Kronecker delta. It's 0 if they are different, if it's 1 if they are the same. It's the same function. And that means if I insert that one in here, the first term I get is 0, 0. That is already 1. And that means all the other ones, so the overlap between any of the corrections with that zeroth order state is going to be 0. That's sort of the consequence of this one. But
why do you say plus or minus?
Oh, that equal, non-equal to 0. Non-equal to 0. So all the other ones, first order, second order, so they are orthogonal to the zeroth order solution. That's a consequence of this one. And it's very useful in deriving the equations, because that means that certain terms disappear. But it also makes a lot of sense, sort of technical, mathematical, a lot of sense, because I'm trying to correct this one. And then, of course, I mean, there's no point to adding more of this in all those corrections. I want to have something else than this one. If you think about vector space, you think about the functions being vectors in the Hilbert space, which is a vector space, and you're trying to represent some kind of a vector. I mean, that's our unknown psi. And now, let's assume that my psi 0 is something like this. So I'm missing the component in this direction. 1 second. Then there's no point in adding a vector which has more components in this direction. That I already have covered. But what I'm trying to say is sort of, I mean, there's the purely making the equations easier aspect, which that leads to. But there's also no point in, if I want to sort of correct this vector in order to get this vector, there's no point to add a vector which sort of looks like this, and therefore has a component in the same direction. I mean, we have this direction already covered. We need the other direction. And that's what this is saying, because we need something which is orthogonal to the first vector.